Good. So I want to acknowledge that this talk is based partly on work with a postdoc, Adam Kobernsky, and then a colleague of mine, Jim Weatherall. And this is really part of a book with Jim that we're nearing completion, which we've called The Aim and Structure of Cosmological Theory. That's a reference to a famous book by Pierre Duhem, The Aim and Structure of Physical Theory. And I'll mention Duhem again in a minute as a philosopher who's sort of setting part of the stage for the questions we're pursuing. But the book is really considering the situation we're in fundamental physics, where we are looking to cosmology to pursue a number of topics in fundamental physics, understanding the nature of dark matter, dark energy, and whatever physical processes occurred in the early universe. And these offer some of our best windows into new fundamental physics going beyond the standard model of particle physics. And we have an enormous amount of observations to draw on from cosmology, largely but not entirely limited to the observations of the cosmic microwave background radiation that the cosmologists have been exploring over the last 60 years and drawing increasing amounts of information from that in order to pursue both the setting of the parameters in the standard model of cosmology and also trying to decode what happened in the early universe. And so the motivation for the book is partly to reflect on, from a more philosophy of science point of view, the challenges to this project of discovering new fundamental physics in cosmology. So obviously, there are a lot of things that set cosmology apart from other ways that people have pursued fundamental physics. It's a reliance almost entirely on passive observations. And often, the physical, the energy scales that we're interested in probing are inaccessible by means other than the cosmological observations. So that, I think, puts us in a kind of interesting situation where we're trying to pursue this research, and we're doing it in a different setting. We have a different kind of domain in which we're trying to pursue questions about fundamental physics. And so the aim of the book project overall is to look at different aspects of the standard model of cosmology, dark matter, dark energy in the early universe, and look at what kind of philosophical principles or ideas guide research in this new domain. So for example, in thinking about the standard model, how do we think about the nature of the cosmological principle? And we also think that there are various moves that cosmologists make in thinking about this area that reflect views about what a satisfying explanation of some feature of the universe should look like, what should count as a satisfying or good theory of a domain, and so on. And so our aim is not really to advocate a different theory or something crazy. I mean, we think that the standard model of cosmology is very well supported by evidence overall, but rather to ask what kind of philosophical views are informing inquiry as it's unfolding in this area. And so today I'm really going to focus on just the one part of this overall book project, looking at early universe cosmology in particular. And so I think one way of framing it is to look back. I mentioned that the title of our book refers to Duhem. So Pierre Duhem is probably not somebody whose name is familiar to everyone except the philosophers in the audience, but he is a philosopher who's, oh, okay, thank you, who is famous for articulating what's usually called an underdetermination thesis, the underdetermination of theory by evidence. That's a little dark, yeah. Yeah. So, and I think one way of putting the question that Duhem was worried about that usually you think of as underdetermination, there's a slightly better way of formulating it, which I'm trying to get at with this quotation. So as he says, every physical law is an approximate law. Consequently, it cannot be for the strict logician either true or false. Any other law representing the same experiments with the same approximation may lay as just a claim as the first to the title of a true law, or to speak more precisely, of an acceptable law. So what I think Duhem is getting at in this passage and in the overall discussion is that there's some element of freedom in representing the phenomena, in choosing exactly what laws you see them as instantiating. So there's a question that you have, which is, how am I representing the phenomena as following certain laws? And how do I see the physical significance of those laws as being revealed in the phenomena? So how then to establish the physical significance of a particular choice you've made in representing the phenomena? And we'll see examples of this later. There's a different question, and this is not as famous. There's a book that Duhem published in 1902 called The Electric Theories of Maxwell, a Historical and Critical Study. So this is before Einstein's 1905 paper, of course. And one of the things that Duhem is interested in this book is evaluating arguments for the existence of an electromagnetic ether. And he argues against the idea that the success of Maxwell's theory actually supports the claim that an ether exists. And so I think this is an example of asking a different question, which is, what aspects of a theory actually contribute to its empirical success? And we might be over-interpreting or misinterpreting a theory to think that, say, the ether is an essential part of electromagnetism, and somehow the success of electromagnetism supports the idea that the ether exists. So these are then, I think, two philosophical challenges we can pose about any area of physical theory. And I also think the other main move that Jim and I make in this, in the book overall, is in thinking about responding to these challenges and how to assess the development of physical theory, there's two different aspects that you can focus on. One is really looking at the initial assessment of a theory or the initial acceptance of an idea. And there, I think the kinds of considerations that are most important involve promise, the feasibility of the idea, whether it makes novel predictions, and so on. So this is, I think, the kind of concerns that are relevant when a colleague proposes a new idea, right? How do you make that initial assessment? But I think for the point of assessing the sort of status of our theories and answering these philosophical challenges, we should instead shift to a different kind of evaluation, a long-term evaluation in which we can ask, how stringently is a theory tested by the subsequent research that is based on it? So once we have a theory in place, it might guide research for decades or centuries. And how is that further work giving us new insight into the foundational principles or providing new and further tests of the foundational principles of that theory? We can also pose this question more prospectively for a relatively new theory, which is, what's the potential for that kind of stringent tests given the available evidence? And so we think that that long-term evaluation or that prospective evaluation focusing on the possibility of having a line of inquiry with that nature as being more revealing and more appropriate for responding to these kinds of philosophical challenges. And I should acknowledge, in thinking of the long-term evaluation, this is really reflects an impact of a mentor and a terrific colleague, George Smith, who passed away about 3 months ago. And there's two papers of his, a paper and a book in particular, that I think articulate this view very nicely. One is called Closing the Loop, Testing Newtonian Gravity Then and Now, which is just a masterful overview of how to think about the status of Newtonian gravity over around 250 years of celestial mechanics. And then also a book that's about the case made for the existence of molecules around 1913 and how the evidential case at that time changed quite dramatically. And so George's work is really informing what we're doing in this chapter. And so the two main ideas that we're drawing out of this, and this is why we called the paper Closing the Loop in reference to an homage to George's paper. What he emphasizes is that we should think of the development of theory as a kind of iterative refinement, a process of identifying novel, robust features of a system that can be independently accessed, that can be independently verified or confirmed, as we have a theory that's getting us a more and more detailed description of a domain of phenomena. And the second is that success in this sense responds to the second philosophical challenge. If you have a theory that's giving you this process, giving you a series of more and more detailed descriptions of a phenomenon, the success in doing so really gives a stringent test of the aspects of the theory that play a role in that kind of evidential reasoning. So it isn't, so you can try to distinguish between free wheels or parts of the theory that are perhaps less secure and the ones that actually play an essential role in this process. So today I'm going to talk about what has really been the dominant working hypothesis about the early universe since really almost shortly after it was introduced in the 1980s, which is the idea that in the early universe, so in the simplest models, the early universe is dominated by a single scalar field called the inflaton field. Sorry, my screen here went off, so I was worried that something had happened, but it looks fine. So in the Simplest version of the hypothesis, there's a single scalar field, and that dominates the early universe dynamics, leading to a phase of inflation. Again, assuming that the inflaton field is in the appropriate state in an earlier region, then it will contribute to Einstein's equation as a false vacuum term, and that will lead to exponential expansion. And this was introduced in order to resolve fine-tuning problems of the Big Bang. Initially, what Guth was worried about was something called the monopole problem. And then there are other features of the standard hot Big Bang model, the flatness and uniformity. Again, this is probably familiar, but uniformity just refers to the fact that if you look at the CMB in different directions in the sky, the temperature and other physical properties of the universe are the same, even though those regions could not have had overlapping past light cones if the standard FLRW models are accurate. So, and it's not that recent anymore, actually. About a decade ago, there was a debate that is something that's occurred repeatedly in discussions of inflation. Although this particular debate, Steinhardt, Eos, and Loeb, I think, chose sort of a way of framing the debate that was particularly meant to provoke advocates of inflation. They had an argument that it wasn't even scientific because it was not falsifiable. That seemed guaranteed to to provoke a response, which it did. And this was an exchange of, there were some papers behind it, but there was also an exchange in Scientific American, which led to, I forget how many, there were several dozen cosmologists who wrote a letter to Scientific American in reply to this claim that inflation was not falsifiable. But I think the background question that they raise is something that is actually, is a question that's popped up in various ways since inflation was first introduced. And the worry is that inflation seems in some ways to be quite flexible. And the worry is it the case that the success of inflation in matching what we see, how much evidence does that give us that inflation actually occurred? And so I think there's an interesting question here, but I would formulate it in a very different way. As I've suggested in terms of a long-term prospect. So what are the prospects for iterative refinement of the inflationary hypothesis that would allow us to probe details of the early universe and discover new robust features? In other words, let's take inflation on board as a working hypothesis. What does it allow us to do? Does it lead to a kind of inquiry that allows us to gather further new evidence that the inflationary stage occurred and helps us understand these details of the early universe? So today I want to say a little bit more about the case that George Smith talked about closing the loop. And I'll come back to see how those ideas play out in more detail in the case that I've just mentioned, the early universe. And then I'll finally conclude by looking at a few different ways you might respond to this way of thinking. Okay, so again, the argument that George gave in looking at Newtonian physics and celestial mechanics was that we can often in physics move beyond just phenomenological success of a theory. So in cases where we can control the idealizations involved in developing a physical model, and we understand the physical assumptions used in them, then discrepancies with observations, which are almost always present, right? We almost always construct a model and then notice that it doesn't immediately match observations exactly. The discrepancies will then be revealing if we have sufficient control over our models. And those discrepancies can reveal further details, and then that can lead to this process of iterative refinement that we can get a successively more and more detailed description of the phenomena of interest. In short, it can lead to a risky and tightly constrained line of inquiry. And so going back to the case that George describes in more detail, you probably haven't heard of any of these figures other than Kepler. But when Newton first got interested in thinking about the solar system, he seems to have been inspired by a few things around a little bit before 1680. There was a comet that he actually did observations of. So this was around the time when he would have been looking at the texts available to see how they give descriptions of planetary motions. And it turns out that in addition to Kepler, so we tend to think of the three things on the top as just Kepler's laws. that wasn't actually a terminology that was introduced until Voltaire. Voltaire was the first to say, here are Kepler's laws describing planetary positions. At the time Newton would have first started asking, well, how do we calculate planetary positions? There were instead a number of different proposals. So everybody recognized that Kepler's proposal that the planets move along ellipses was better than anything that had gone before. So the trajectories are all ellipses. But the actual way of trying to calculate the speed along the trajectory or where they're located at different times ends up being more complicated. And so there were several different proposals, several different ways of representing the planetary motion that correspond to these different constructions. Now, the important point, this goes back to the point from Duhem, that often you have a number of different ways of representing the phenomena. You have different mathematical constructs here, and you have a choice of which one to take as being interesting or which one is physically significant. And of course, Newton's key insight was that once you understand the dynamics, once you understand how to characterize force, that singles out Kepler's laws as just reflecting consequences of a central force. Right? So this particular way of representing the phenomena is different from the others because it is tied to the underlying dynamics. So in other words, we move from just a mere phenomenological description, which is, as Kepler gave in Astronomia Nova, this is his first illustration for the orbit of Mars. We can go from a phenomenological description that just says the planets go along approximately Keplerian orbits to saying with Newton that we can think of the planets as governed by the gravitational interaction, and we can think of all of the solar system motions as a form of n-body gravitational interaction. So we can model the system as just that kind of problem. And that has obviously, a ton of further implications once you treat them as moving under the gravitational force. Now, George describes in detail how this plays out over the development of celestial mechanics, but the real central point in terms of the evidential reasoning involved, I think, is captured nicely in this quote. So he says, Newton's Principia forced the test question within orbital astronomy for his theory of gravity to be not whether calculated locations of planets and their satellites agree with observations, but whether robust physical sources can be found for each systematic discrepancy between those calculations and observation, with the further demand of achieving closer and closer agreement with the observations in a series of successive approximations in which more and more details of our solar system that make a difference become identified along with the differences they make. So one thing that George notes in this paper is that there's only about a 1-decade period in the entire time from 1687, when Newton published the Principia, up until the early 20th century with Einstein's general relativity. There's only about 1 decade when there weren't known anomalies, that there weren't known discrepancies between observed motions and the best fit models that astronomers had developed up to that point. But as he emphasizes, the point is not whether there are anomalies, it's that anomalies drove sorry? It was, I don't know, so it was in the late 18th century, before, I believe, the discovery of the secular acceleration of the moon. Although, don't hold me to that. It was, yeah, that's why I said 18th century, not 19th. So yeah, certainly the once you start seeing the perihelion motion of Mercury, that's something that starts in the 19th century. But what I don't remember is there's the secular acceleration of the moon, which was a problem much earlier. And it was, I think, before that was discovered that there was a brief period. So apologies that I don't know off the top of my head, but the overall point is that throughout this history, there were always anomalies. Sorry? Things never work, exactly. But they can guide the development of theory. And so if you look at so what does George mean by robust sources? Well, the most obvious one is Neptune. You can see the planet, the orbit of Uranus isn't quite what you'd expect, and then you can project that if there was another planet that was further out, it would cause exactly the kind of perturbations that would fit with what you see in Uranus's orbit. There are more subtle cases, the secular acceleration of the moon, and then there's something that was not really resolved until the 20th century, It's called the great empirical term, which is really just there's a varying rotational velocity of the Earth that has to be accounted for in order to get the planetary observations to match at the level of precision that was then available. Again, in each of these cases, the important point is that you could independently check. Neptune is just the easiest case. You can point your telescope and see whether it's there. Each of these others, though, you have discovered a detail about how the solar system works through understanding the gravitational interaction among the planets. But then you can independently see, and this is really what the emphasis on robust source means, you can independently see whether it is in fact the case that the Earth's rotational velocity is changing. And so I think this kind of development gives you a really clear and effective response to the philosophical challenges I mentioned before. So the worry about underdetermination, well, we've been able to identify the physically significant features of planetary motions. And we have to qualify that. It's at some level of approximation within a suitably restricted domain. So there might be, as we extend to new domains, we might have to reconsider how to characterize those, but we've adequately identified the physically significant features. And we also are able to say that there's a clear contribution of theory. We can say that there are aspects of the theory that play a role in uncovering these new robust sources. So what components of the theory were actually important in the inferences where we discovered a new planet or we discovered some other subtle feature of the solar system that we had to account for as we developed our more and more detailed description. And so when we have this kind of success, I think we have a very compelling response to the kind of skeptical underdetermination worry that philosophers often raise. And in some sense, I would say we can, if we have a theory that meets the kind of standards I've articulated, again, very briefly, we can make the case that the theory makes a permanent contribution to our understanding of nature, that we should, and obviously this is something Einstein demanded when he was creating a general theory of relativity, that there's some sense in which the Newtonian theory was recovered as a limit case of general relativity. And if we have the kind of reasoning that I've described, I think it's appropriate to make that kind of demand, that we should demand that we recover the evidential reasoning. What I mean is we recover how it is that the theory played a role in developing this more and more detailed account of the solar system, and are able to say why that is still valid, even though the nature of gravity is not the way Newton described it. Okay, so that's the warm-up case in which we have the benefit of hindsight to see how things worked out with Newtonian mechanics. And so my proposal is that we can pose a similar kind of question regarding the early universe. And this would, paraphrasing Smith's earlier formulation, the question for early universe cosmology is not just whether observed features of the early universe, including the overall uniformity and temperature anisotropies in the CMB, can be fit with a particular choice of the inflaton field, but whether robust physical sources can be found for each systematic discrepancy between calculations and observation, with the further demand of achieving closer agreement with observation in a series of successive approximations, in which more and more details of the early universe that make a difference become identified, along with the differences they make. So what are the prospects then for an iterative approach to early universe cosmology where we can build up the same kind of evidence that we have built up in the case of celestial mechanics? So obviously, there's a wealth of observations that have been made, a wealth of data from observations of the CMB over the last 60 years since it was first discovered. And so we have a description of the phenomenology of the CMB temperature anisotropies, that they are well described as Gaussian, linear, nearly scale invariant, and adiabatic density perturbations. And then we have a proposal for the physics underlying these features of the CMB, that they reflect the dynamics of an inflaton field at an earlier phase of the universe's history. And the question then is, what are the further implications if we take the inflaton field to be the underlying physics describing this phenomenology? Again, this is probably too much of a review for this audience, but a very simple kind of inflationary model has a single scalar field, and It's described by a Lagrangian such as this with an effective potential, and then it has to have interaction terms with other standard model fields so that after a phase of inflation, it will then it will decay and repopulate the universe with other kinds of fields. And usually, sorry, for slow roll models, I don't know if this might not have any batteries. Yeah, anyway. So for a slow roll model, you have a field that while it's on the flat part of the potential, it will be driving an effective, it will act as an effective cosmological constant and drive a phase of de Sitter-like expansion. And a sufficiently long phase of de Sitter-like expansion will then solve the flatness and uniformity problems. And then fluctuations of the field in the vacuum state are described, the evolution of those is described by the Mukhanov-Sasaki equation, and it has a characteristic evolution where for sub-Hubble radius modes, those will just oscillate. For super Hubble radius modes, those will freeze out, and those fluctuations, sorry, I might have this on the next slide, those fluctuations will freeze in and become the source of density perturbations. So we can think of inflation as having three different stages. The first is the part where there be dragons, or quantum gravity in this case, a pre-inflationary stage where we think the energy scales are high enough that we might need to use quantum gravity to describe the system. But as long as there's some part of that system that has appropriate conditions for an inflationary phase to start, there'll then be a phase where the inflaton field drives this expansion. As I mentioned, there's horizon exit and re-entry of the fluctuation modes of the inflaton field that lead to these characteristic features of the density perturbations. Those depend on the features of the potential. And then finally, there's a phase which is called, well, first of all, the graceful exit and also reheating. That's sort of the phase at which we have the inflaton field decaying into all the other fields in such a way that we can set the stage for the standard hot Big Bang model. And we can ask, I'm going to skip over this. This is, because it's quite complicated, the only message I want to convey is, and this is actually already 7 years old, but the Planck data from the CMB are able to take the space of models of different types of inflation and then constrain the parameters appearing in those models based on the observational features of these primordial perturbations. In particular, their tilt, the tilt of the spectrum, and the tensor to scalar ratio. And so these are just sort of confidence intervals for a number of different types of inflationary models. So overall, you have a space of different models, well over 100 distinct models or types of models. And then for those, you can use the observations of the CMB to constrain the parameters appearing in those models. And if we accept inflation as a working hypothesis, then we can characterize the physical significance of these observations as follows. So the fact that the CMB is uniform, it has the same features in different regions, really just reflects how long the inflationary expansion lasts. The temperature anisotropies, the sort of detailed fluctuations in the CMB, those are fixed by the features of the inflaton potential at the stage where the fluctuation modes exited the Hubble radius that are then imprinted as density perturbations. So you get a constraint on a part of the potential, how both the potential itself and then its derivatives. And that's usually, this is somewhat model dependent, but it's a certain amount of time before the end of the inflationary phase. So there's like one part of the potential that's constrained by these. And finally, and two other points, if you observe B-mode polarization, that allows you to determine the tensor to scalar ratio. That will determine the overall energy scale of inflation. And finally, reheating depends on the shape of the potential and the interaction Hamiltonian that is at the end of the inflationary phase. So one thing you can see is that we have a way of interpreting all these different features of the CMB as reflecting different aspects of the underlying dynamics during the inflationary phase. And obviously, if we have a model where we identify the inflation with a specific field, if we say it's a field that particle physicists have proposed in a different model, then we'd have a number of other constraints on the inflaton from the whatever particle physics context it has been proposed in. Now, this is already quite old, but in Weinberg's textbook on cosmology, he says, the consistency of observations with a large class of inflationary models is encouraging because it supports the general idea of slow roll inflation, but also disappointing because it shows that these observations so far do not really tell us anything specific about the details of inflation. With further improvements in experimental precision, we can look forward to a more decisive test of theories of the early universe. So I think the worry that Weinberg is framing here is, so I've given you a sense of what the physical significance is of different features of the CMB. If we accept inflation as a working hypothesis, the question is, how detailed is the picture that we get? Do we know enough to have a detailed picture of inflation and how that will guide further inquiry if we accept that kind of account? So we definitely have phenomenological success. There are many inflationary models that are compatible with the current CMB data, and these imply constraints on the properties of the candidate fields for the inflaton. So it tells you a bit about the properties of the inflaton field or its effective potential. But it's not clear whether we have discrepancies with robust sources that will help us to drive further development of inflationary models. And I think this is reflected in different ways of characterizing a criticism that's been pretty common in the literature on inflation. This is from Keith Olive, a review article about a decade after the idea of inflation was introduced. And he says, a glaring problem, in my opinion, is our lack of being able to fully integrate inflation into a unification scheme or any scheme having to do with our fundamental understanding of particle physics and gravity. An inflaton as an inflaton and nothing else can only be viewed as a toy, not a theory. So this was about 10 years into the development of inflation, and he was unsatisfied with the models that were then available. He thought that they didn't give you a clear understanding of how inflation was incorporated into particle physics. More recently, inflation is often treated as an effective field theory, so a low energy effective field theory describing fluctuations over the background quasi-de Sitter state, which are coupled to Einstein gravity. There are some challenges here as well about, let me focus on the last point, the UV sensitivity of inflationary EFTs. So one of these is called the eta problem, which is in order to construct an inflationary model with a very flat potential, that looks quite unusual from the EFT point of view. So usually you'd expect corrections that come from higher energy scales to change the shape of the potential, and it's hard to maintain a really flat potential. So again, if you describe inflation as an EFT, there's further questions about how can it fit within a more complete account of physics at these scales. So in other words, in terms of the discrepancies with robust sources, I think there's a problem if inflation is really just treated as an inflaton that is constrained only by the cosmological observation. There's a lack of constraints on the inflaton. What I mean is constraints from other ways of embedding it within physics. And so in that sense, we can always go back to the drawing board in light of any discrepancies. So the modeling framework doesn't sort of force you to undergo a process of iterative development. It's always possible instead to just say, I'll pick a different version of inflation that is fixed by the data. There are other sources of flexibility. I'll just mention these in passing because some of them are more important for different critics. So the discussion in Scientific American that I mentioned at the outset by Steinhardt, Ehas, and Loeb, they're actually really focused on the second question, the nature of eternal inflation and the measure problem. So right, they saw that as a different source of flexibility in standard inflationary model building. Briefly, the idea is, and a number of people who accept inflation accept that generically inflation will lead to a multiverse in which conditions vary considerably in different regions of the multiverse. And what that means is there are pockets that have undergone inflation and lead to slightly different physical features as the output state in different regions. And Eos, Steinhardt, and Loeb point out if that's the picture, then it seems like you have another source of flexibility here, and it's much harder to see how you could pin down the features of inflation if you have eternal inflation as the account that you accept. So that's again something that I think is a distinctive source of worry. And let me say there's yeah. I'm coming to that actually. So yeah, maybe we aren't going to get it. So this is, I think there's two different things that we could acknowledge. One, our limitations, right? We're creatures who have a very physically limited position in the universe. So the kinds of evidence that we're able to gather are really limited by the kind of creatures we are. And we might not be able to look at all the kinds of things that would be essential to determine what the correct physics of the early universe is. That might just be an inherent limitation that we're not going to be able to overcome. So that's what I mean by inaccessibility to us of novel further consequences. It might be the case that we have theories of the early universe that say a lot of things about physics that, aspects of physics that we'll never be able to test, right? But I do think there's a distinct kind of question, which is it instead a limitation of the theory? Have we formulated a theory such that features of that very theory form an obstacle to gathering further evidence in its favor? That it's so flexible or that it's unconstrained that by virtue of that feature, we're not going to be able to gather further evidence. Right? So those are distinct kinds of obstacles we might face. So we might have a theory that's very definite and gives us all kinds of predictions at scales or domains that we're never able to test. Or we might have a theory that doesn't actually give us definite predictions because of flexibility in the way that it's formulated. So I think it's important to acknowledge those two distinctive sources of limitation. And then I'm coming now to my closing slide, and I just want to say, sum up with a few responses to this question. So can we close the universe in early universe cosmology? Perhaps I'm posing the question that, this is just too soon. I mean, we looked at the case of celestial mechanics. We had the benefit of looking over 250 years of history. We're only a few decades into exploring the early universe seriously. So maybe we're just still at an early stage of inquiry, and we do have prospects to reveal and constrain the details of inflation. But I think the flexibility of current inflationary modeling threatens the possibility of risky constrained further inquiry that was essential to the way celestial mechanics progressed. Another response is, I think the most optimistic response, is that we can continue to try the very challenging project of integrating inflation with high energy physics or quantum gravity. And that this might give us stronger constraints on inflationary model building. And the fact that inflationary model building, such as inflation as an EFT, still seems to be very sensitive to UV physics, you can treat that as an optimistic note rather than a source of problems, namely that it actually looks like inflation is sensitive to physics at very high scales. And that might mean that ideas about quantum gravity will have an impact and perhaps provide a source of constraints on early universe physics. Finally, and this is something that has been advocated quite explicitly in philosophy of science circles, maybe we should just say that the rules of the game have changed completely. And this is Ricard David in a 2013 book, which is a kind of apologia for string theory, argues that we should think of what we're doing as a kind of post-empirical science. And so this isn't quite the way that David would characterize his view, but the way I think of it is that for some domain of physics, relevant phenomena are inaccessible, and maybe we should regard theories of these domains as at best how possibly accounts, or maybe we should grant them some other status. David argues that we should still think of these as theories that we trust, even though in some sense we don't have any direct empirical evidence for them. So I think that would be quite a dramatic change in thinking about the status of our theories. But it is something that philosophers of science have been debating in light of these developments within physics. So with that, I'll wrap it up, and I look forward to your questions. Thanks. Yes? Okay. Mm-hmm. 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 Yeah. Well, let me ask you, so is there any problem with the standard model of particle physics? Is the hierarchy problem a problem? Okay. But you just said we can treat it as an EFT, or that we should be, yeah. Mm-hmm. Yeah, dark matter, dark energy. Yeah. But so what I want to probe is, so if you say we should just treat everything as EFTs, and that gives us freedom to dismiss certain types of questions. I'm curious what types of questions are within your hand waving there. So I agree that treating things as EFTs has been incredibly productive, but there are still EFTs that have features that seem to reveal a kind of sensitivity to higher energy scales. So there isn't the clean decoupling and scale separation that you do. Mm-hmm. 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 Yeah, and I'm saying that in the case of inflation treated as an EFT, there's a hopeful view that there are features of inflation as an EFT that seem to reveal the same kind of UV sensitivity. Mm-hmm. Yeah, non-Gaussian entities, yeah. Yeah. Mm-hmm. 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 Mm-hmm.
going on. I really wonder whether the problem is astrophysics and cosmology is so far ahead of physics
Hmm.
to understand but probably is somewhere around scale,
Mm-hmm.
10 to 60 GT or so.
Mm-hmm.
Without the theory of gravity,
Mm-hmm.
how can understand which
Yeah, yeah. Mm. Mm-hmm.
So I wonder if philosophy now the time there's no question that cosmology right now is huge about it
Mm-hmm. Mm-hmm.
polarization of meanwhile the Desi and surveys
Mm-hmm.
are probing the evolution of our entity and we continue to learn more and more. And we keep finding that the standard model of cosmology is incredibly robust.
Mm-hmm.
And it's not a book that is the predictions of outbreak were made in 1982, well before they were measured. And now they are measured with accuracy.
Mm-hmm.
So you have to say it's been spectacular. I think you're asking to get physics
Mm-hmm.
to the place where right now physics is so complex. The string theory is supposed to be
Mm-hmm. Good. Yeah. So let me reframe and say, so I think the way I would describe, so first of all, you pointed out a few things that are absolutely right, which is that there's all kinds of other ways cosmology is pushing forward with large-scale structure, and so I neglected that here just for because I don't have the time. But the way I would, so I'm curious whether you think this is an appropriate description. We have a working hypothesis of what the physics in the early universe would look like that's phenomenologically successful. It allows us to understand all of the features of the CMB as consequences of an earlier phase of evolution. My claim is that because we don't fully understand the physics of that, it's still a kind of phenomenological model. And if we had a better understanding of the physics, then we'd have a more constrained model and we'd have much stronger evidence for it. And that's the contrast with other cases in physics. And it's not necessarily that we have to have a comprehensive theory, right? It isn't that you have to have a final theory of quantum gravity necessarily. There are other cases where you still have a theory that is only partial. And this is, I didn't talk about the case of establishing molecular reality in around 1913, but I think as of 1913, well before the advent of quantum physics, you had a very convincing case that there were localized bits of matter that behaved independently that you could call atoms, even though you didn't have a full account of their vibrational degrees of freedom and all kinds of other features that you'd have to wait for quantum physics to develop. And so I think you can have a kind of over-constrained characterization of the physics of that, of a domain, even without a comprehensive account. And what I'm saying is that we have a successful phenomenological model, but I think the claim that we've understood the physics of inflation in detail is undermined by the enormous flexibility we have in model building.
So we're back.
Yeah, yeah.
Where we are today.
Mm-hmm. 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 Right. Exactly. We don't have the clear understanding of the physical significance of the phenomenological description that Newton gave us for Kepler. Yeah. Yes. Yeah, so I guess it depends to some degree on your view of quantum gravity and how much of a mess physics is in, to go back to Andrew's question. So the hope is that if you had a way in which inflation was sensitive to the details of quantum gravity, that would give you a source of further constraints on the physics of inflation. So the empirical constraints don't seem to be sufficient to resolve the sort of degeneracy in the model building. You have a huge space of models that are all compatible. If you had complete, like maybe if we observe non-Gaussianities or if there are other sorts of observations, those might be able to break the degeneracy. But we've essentially got just a few numbers, and we're trying to then constrain the modeling space with those observations. So I didn't want to say, it's not that I wanted to say that the empirical case couldn't ever narrow the window down. It's just that given what we currently have, there seems like there's a huge space of models that are compatible with the observations that we have. Yeah, yeah, and the fact that it's UV sensitive just means that it does seem to depend on physics at higher energy scales. If it completely decoupled, then you'd worry that the EFT of inflation wouldn't be sensitive to quantum gravity effects, and then, yeah. Yes? Mm-hmm. Ah. Okay, so yeah, this is a common move where you say, I have some sort of theories that apparently differ, but they actually all give me the same results. So let's just treat them as an equivalence class and treat them as sort of, given the observations that I have available to me, I'll just say they're all equivalent. Is that the move you're making? Yeah. Mm-hmm. Mm-hmm. Right, right. No, I mean, I've had, cosmologists take the line, just take the CMB as, that sort of, take that as setting the initial conditions for your cosmology. You don't understand the causal processes that generated that, but for the rest of cosmology, you can take, I'm not advocating this view to be clear, but this is the kind of view that some cosmologists have said, like, look, you might want to understand the physics that led to the CMB, but in terms of subsequent evolution, very little of what happened in the early universe is going to be relevant for other domains, right? We don't expect, if there is an inflaton field, that it will be relevant in describing other experiments later on, because it will be dynamically irrelevant at later stages. So if that's your position, then yeah, I think you can say there's an equivalence class of theories that as far as we can see are compatible, and we just won't ever be able to distinguish between them. And the choice among them doesn't matter to us because it doesn't come in any other description later in the universe. And I think that's a position that's totally, it's hard to argue against. I mean, it does sort of fall short of, I think, the hope of being able to say, here's the process that unfolded in the early universe. Mm-hmm. Mm-hmm. Sorry, I just didn't hear that. Mm-hmm. No, that's true. You can adopt a kind of quietism and say there are certain questions that we shouldn't expect to have answers to, or actually can prove that we wouldn't have answers to. This would be a different kind of case, I think, that you're saying, given the the physics that's accessible to us or the kinds of observations we can make. There are just certain kinds of questions that we'll never have complete answers to. Sorry, we should talk afterwards. I don't think I've completely understood. Yeah. Yes. Well, I don't think it can give you vector. So you can really only have scalar and tensor perturbations, and they're linked by a consistency because they're generated by the same mechanism. So there are sort of things that are quite specific of the inflationary mechanism. So if you ask, can you have scalar and tensor perturbations in an arbitrary rate? So I'm a little worried because there are so many different inflationary models that maybe there's somebody who's come up with one that will violate this. But there's a few kind of standard claims that you have this consistency relation, and because the scalar and tensor perturbations are generated in the same way, you can't just sort of arbitrarily tweak them, right? So I don't want to make it seem like inflation is compatible with everything, right? So I wasn't making that claim. Yes? Mm-hmm. Mm-hmm. Well, so I don't think I'm I mean, some of your colleagues will give a better answer to this than I will, but I think there are a number of things people are looking for, like non-Gaussianities and B-mode polarizations, sort of more information from the CMB that will help to constrain inflationary models. So I think those are sort of, maybe there's some other ones that are more subtle that we could look to, but the question that I'm posing is, are there any things, so again, if you're interested in using discrepancies to learn more about the details of the physics, you have to have some kind of constraint on the model building so that a discrepancy will not just be something that you can respond to by shifting to a different model. And so the model space itself is so large that I don't think there's any phase of development where people have said, here's the Higgs inflation model with non-minimal coupling. If there's a slight discrepancy, then we'll actually refine that model and say that we've discovered something further about the early universe, as opposed to just say, go back to the drawing board and say, well, that was just evidence that the Higgs field non-minimal coupling model wasn't the right way of doing inflation. So that's the contrast that I want. Well, I think there are some observations that would be incompatible with like the large space of, like if you had a tensor to scalar ratio that wasn't consistent. Certain kinds of, I think there are certain kinds of things that would be incompatible with all of them. But I don't have prescriptions for specific further observations that we should pursue. And I don't think I should be, I mean, I'm the philosopher here. I'm not going to be telling people exactly what the most promising observations are.